All right, so let's continue. All right, lemma 17, which is Bezout's lemma. It relates the GCD to linear combinations. So if you have the GCD of two numbers, a and b, you can represent that as a linear combination of a and b with integral coefficients. Basically, what that means is if you take the GCD of a and b, it is always possible to find integers x and y such that you multiply a by x, you multiply b by y, and you add them, and you get the GCD. Right? This is always possible to do that. So if a and b are relatively prime, then it's always possible to solve to do this, meaning that there is a solution to this equation in terms of x and y, if you know what a and b are. Right? And this here actually gives you what the solution is. Lemma 19 tells you how to solve that an equation like this. So, well, okay, so not just an equation like this, but a more general equation than that. So if a and b are integers, right, and the GCD of those two integers is d, we're going to consider this equation, ax plus by is equal to c. This is any equation or the form ax plus by is c, where we know what a and b are. And, well, we know what c is. C is some integer. The x and the y here, the unknown variables that we'll have in the equation. And that's what we're trying to solve for, x and y. So there are two cases to consider. First of all, if d, which is the divisor of a and b, does not divide c, it means there's no solution. Which is, if you think about it, it makes sense, because if d divides a and d divides b, it divides the left-hand side, but I'm saying that d does not divide c, so it doesn't divide the right-hand side. And that is a contradiction. So the equation would have no solutions if d, which is the GCD, does not divide c. If d does divide the GCD, if d, which is the GCD, does divide c, it means that there will be infinitely many solutions. And those solutions are of this form here. Now, how you do this is basically, first thing you have to do is find a particular solution. A particular solution basically means you have one solution that works. So you just what you do is basically try values until you get one that works. And that pair, you call that x0, y0. So using this pair, you can get the general solution. Basically, x would be x0 plus or minus something, and then y is y0 plus or minus something. So this minus sign I have here, first of all, let me mention that this minus sign doesn't have to be here. The minus sign could be here as well. Right? You could have plus here and minus here, or minus here and plus here. And the reason being is that k is an arbitrary constant. So you could have actually taken the minus sign into k instead. Right? So I'll show you an example here. So basically, once you know what x0 is and what y0 is, you can write the general solution. X would be x0 minus k times this, b over d. And then y is y0 plus k times a over d. Right? Again, you could put a minus sign here if you wanted, but then here would become a plus. Right? And how I usually remember this is you have the particular solution at the start, and then you plus or minus k, depending on which one. You just put the minus in one of them, the plus in the other one. And then what you do is you take the number not associated with x. So here I have ax, right? So the b is associated with y. So I take the number not associated with x, so that would be b, and divided by the GCD. And similarly for y, I take the number not associated with y, that would be a, and divided with d. Right? And you could actually show that this works. If you take these two expressions and substitute back into this equation here, you'll see that this term actually cancels with this term when you substitute. So what you end up getting is basically a times x0 plus b times y0 is equal to c, which you know works because x0, y0 is a particular solution, meaning a solution that works. All right, lemma 20, if a and b are positive, where a is more than b, right? If you use the division algorithm, so you write a is bq plus r, then the GCD of a and b is the same as the GCD of b and r, right? B is the smaller one, so you want to take the smaller one. This is actually something we used before when we were calculating GCD. right? Now there's something else called the Euclidean algorithm, which lets you find the GCD of two numbers in using our algorithm. So I wouldn't explain the algorithm in theory. I'll just do it through this example. So how it works is you want to find the GCD of, let's say, these two numbers. So you start with these two numbers, right? What you're going to do is use the division algorithm on these two numbers and find R, right? So you're using lemma 20 here. You're using the division algorithm and you find an R, and then you're taking the GCD of these is the same as GCD of the smaller one with R. So if I use the division algorithm with, well, across here, 168 is 98 times 1 plus 70. So R is 70. So the GCD of these two is the same as the GCD of the smaller one, which is 98 and R, right? So that's how I get these two numbers. And then I keep going from there. So I do the same thing with these two. 98 is 70 times 1 plus 28. So the GCD of that is the same as the GCD of 70 and 28, right? And this is equal to this. So there's actually equal signs over here going on. Right, and keep going. So next we have 70 is 28 times 2 plus 14. So it's the same as the GCD of 28 and 14. Now, at this point, you actually know that 28 is 14 times 2, right? So the GCD of these two would just be 14. But you keep going until you get a 0, basically. And once you get a 0, the last positive value you got for R would be the GCD. So if I look at these here, right, the last positive value I got for R is 14. That would be the GCD. If they were relatively prime, the last positive value you get would be 1. So you would know that the GCD is 1. So that's how you find the GCD. Now, you could actually use these equations that you use here and work backwards to get the linear combination, meaning you work backwards to get the values for X and Y that we had up here. So how you work backwards, right, is you start with the last one that doesn't have a 0. So you start with this one. And what we're going to do is I'm going to write the GCD, which is 14, because I know that's the GCD. 14 is 70 minus 28 times 2, right? So that's this down here. And then what I'm going to do is this 28, I'm going to go up to the equation above and write that 28 in terms of these two expressions. So 28 is 98 minus 70. Right? I don't need to write it times 1. I just put it there so you'll see that it comes from the equation. Right? And then you go up again and you say, well, okay, 70 is this minus this. And you basically do that. Be careful when you're simplifying, right? Because it's easy to simplify some of these things, but you don't want to oversimplify because the idea is you must have these two numbers in the end. So if you had, for example, where is it? If you had simplified this expression, you wouldn't actually get what you want because you wouldn't have these two numbers anymore. You would have 70. Right? So anyway, once I finish that, I would get that 14, well, down here, 14 is equal to this. Meaning that if A is 168 and B is 98, the GCD is 14, and then the numbers I have is X is 3 and Y is minus 5. Right? So that's one solution. Now, like I said, there's infinite solutions to this, right? So this isn't the only solution that works. This is just one solution. And actually, you could use the Euclidean algorithm to find this one solution, meaning that here, this particular solution could be found using the Euclidean algorithm. Right? So once you find this, you could use lemma 19 to write a general solution like this. There was actually a typo in the original version of this notes. These were reversed, so I had to fix that. Right? So it means that, so remember, plus 3 and minus 5, there's a minus sign here. So minus 5 would be the particular solution. So x0 is 3, y0 is minus 5. Right? And remember, for x, so this is the equation we're looking at. For x, we're looking at the coefficient that, basically the coefficient of y, the other term. So I have 98 divided by the GCD, which is 14. And then for y, I have the other term, which is 168 divided by GCD, which is 14. So simplify that, you get these two expressions here, and this is the general solution. So you could try, no matter what the value of k is, you'll get a solution. When k is 0, I'll get back the original 1. I'll get 3 minus 5. When k is 1, I'll get minus 4 and 7. So you could try that. Minus 4 times 168 plus 7 times 98 will in fact give you 14. Right? And any value of k is substituting here will give you a solution. There are, like I said, there are infinitely many solutions. All right, so yeah, these are some exercise questions you can try. I think I'd mentioned this before, just as a hint, if you want to show something a fraction can't be reduced any further, what you're basically trying to do is show that these things are relatively prime. All right, so just find the GCD of these two numbers and you're done. And this was an IMO question back in 1959. So if you were lucky to be in the IMO in 1959, you would have gotten a very easy question. All right, so that's it for GCD. The next thing we have to look at is prime numbers. So an integer p greater than 1 is a prime number if it has no positive divisors other than 1 on itself. If it does have multiple positive divisors, then it's called composite. Right, and 1 is neither prime nor composite. So this is just a list of the first 100 prime numbers. Lemma 26 says every integer greater than 1 has a prime divisor, at least 1, right? It has at least 1. If it's prime, then it's only 1. If it's composite, then it's more than 1. Lemma 27, if the product of two prime numbers exceeds n, then the two prime numbers cannot both be factors of n. Again, that's intuitive. If you take two prime numbers and multiply them and you get a number bigger than n, it means that both of them can be simultaneously factors of n, right? Because the product is bigger. But you really do need to be careful about making statements like that though, because this only works if it's prime. So there's a note here. If the numbers were not prime, this doesn't hold. For example, 8 times 6 is 48, all right? 48 is bigger than 24, but 8 and 6 are both factors of 24, right? So it doesn't work if they're composite. A lot of these statements only work for prime numbers.
Jags.
Yeah.
But wouldn't that statement work for any two numbers that are relatively prime? Composite?
Yeah, it would. You're correct, it would. It's just if they're relatively prime, it would. So this, you could expand this further and say if product of two relatively prime numbers exceeds n, then they can't be both factors of n.
Okay, cool.
Yeah.
So then if the two prime numbers are the same, then that wouldn't work then.
Well, if they're the same, then they're not relatively prime.
Right, yeah.
We're saying in this statement, if the two prime numbers are the same?
Yeah.
Yeah. I guess this should be amended then. I'll have to make a note of that to fix this. But I think when I say two prime numbers, yeah, it's not explicitly stated, but it's implied that they're different prime numbers.
Yeah, right.
But you're right. I should clarify that. So I'll make a note of that. This should be two distinct prime numbers. Or I guess if we go with relatively prime, like Alex suggested, then that would fix everything. So could just put in here if the product of two relatively prime numbers. All right, theorem 28 is useful when you're trying to show something as a prime number, right? If n is a composite number, then n must have at least one prime factor not exceeding the square root of n, right? This again is intuitive because if it's composite and you look at the square root of n, there must be something less than or equal to the square root of n multiplied by something greater than or equal to the square root of n to give you n. Right? All the factors can't be greater than the square root of n because when you multiply the two of them, you'll get a number bigger than n. So then they can't be factors. So how you use this is if you want to try to show something is a prime number, then basically you find the square root of that number and then divide n by all the prime numbers less than or equal to the square root of n. Right? So for example, if I wanted to test whether 311 is prime, what's the largest perfect square less than 311? Come on, somebody figure it out. What's 18 squared? 18 squared is bigger than 311. 17 squared is what? 289? Or something like that. Anyway, 17 squared, 17 is the largest one. So if you wanted to show that 311 or check whether 311 is prime, what you're going to have to do is divide 311 by all the prime numbers less than or equal to 17. Obviously, 2 and 3, you could check 3. The digits don't add up to 3, so that doesn't work. A multiple of 3, I mean. 5 doesn't work. 7 doesn't work. 11 doesn't work. 13 doesn't work. And 17 also, I think, doesn't work. I'm not sure. $17 doesn't work. So 311 is prime, right? And that's how you would do it. You don't have to actually go and divide by all the prime numbers less than n. You just go up to the square root of n. Oh, there's an example here. Didn't realize that. So yeah, you could check this one as well. Euclid's lemma, if P is prime and P divides a product of two numbers, then either P divides one or P divides the other. This is one where, again, you have to be careful. If P is composite, this is not whole, right? So if you take P is 4, A is 6, and B is 2, then 4 divides 12, but 4 doesn't divide 6 and it doesn't divide 2. So be careful with that. Only if P is prime, then you can make this statement. And you can extend this to any number of numbers. If P divides A, B, C, then P has to divide one of them. All right, that's the extension there. Fundamental theorem of arithmetic. Every positive integer greater than 1 can be written uniquely as a product of prime numbers. Right? You can have prime where the prime numbers are repeated if necessary. So using that, you can have what is called prime factorization, right? This is useful when you have things with factors and numbers. So basically you could write n as P1 times alpha 1, where P1 is the smallest prime factor of n raised to some power alpha 1. And then you keep with. So P2 to the power of alpha 2 and so on. Right? The alphas are the powers of the primes. So for example, I could take 600 and I could write it as 2 cubed times 3 times 5 squared. All right, this is the prime factorization of 600. You would have to like manually long divide this to get all the different factors if you wanted to. So for example, I know it's even, so I start by, well, the last two digits is 0, 0, so it's divisible by 4 for sure. So I could divide it by 4 and then see what happens from there. Or divided by 5 or whatever you want. But well, actually this is more easy to do than most because it's just 100 times 6. So once you prime factorize 100, you prime factorize 6, you just multiply together. This here is pretty useful to know the number of positive divisors of a number n with prime factorization given here. Well, how you find that is basically take the power and the powers, add 1 to them, and then multiply that. So for example, the number of positive divisors of 600, remember 600 is 2 cubed by 3 by 5 squared. The number of the positive divisors would be 3 plus 1 times 1 plus 1 times 2 plus 1, which is 24. Right? You could actually list them out and check if you want. how this works is actually a combinatorial argument, because for every one of these powers of the primes, you can either include that power in the divisor or exclude it. So you have two choices for each of the powers, right? So meaning you have two choices for, I guess, 2 squared, 2 cubed, and so on, 3, and then 5 and 5 squared. And then there's also the case where you exclude all of them or you include all of them. So that's an extra 2, extra 1. That's why it's always plus 1, right? So you can either go 2 to the 0, 2 to the 1, 2 to the 2, or 2 to the 3. So you have to add the 1 to include the 0 as well, 0 power, right? And then you use the product rule. So basically you have 3 plus 1, 4 options. And then you have 1 plus 1, 2 options, and then 2 plus 1, 3 options. So it's 4 times 2 times 3 will give you the answer. Right, this one is useful as well. The number of multiples of a number m not exceeding another number n is given by the floor of n divided by m. So basically, if n is a bigger number and you want to know how many multiples of m there are from 1 to n, then you divide n by m and then you look at the greatest integer less than or equal to that, and that would give you the answer. For example, the number of even numbers from 1 to 99, you divide 99 by, it's even, so we're looking for divisibility by 2, so you divide 99 by 2, all right, and you'll get 49.5, but we want the floor of that, which is just 49. The number of positive multiples of 5 not exceeding 2 to the 7, again, you divide 2 to the 7 by 5, and you'll get, when you take the floor, you get 47. Right. Apart from 2, every prime number is either of the form 4n plus 1 or 4n plus 3. Right, for some positive integer n. This is important, apart from 2, because 2 can be written as either of those. So how this works is, remember, well, there's a proof here, but basically every number can be written in one of these 4 forms: 4n, 4n plus 1, 4n plus 2, or 4n plus 3. 4n is clearly not prime because it's 4 times something. Right? 4 itself is not prime. This thing here is divisible by 2. Right? So the only way this thing is prime is if n is 0, which gives you the number 2. So the number 2 comes from this case. There's no prime number in this case. And you're left with the other 2 cases to consider. So it's either 2 or one of the other 2 cases. You could do something similar for 6, right? I think that's in the exercise. You all could think about that. This is just a note here talking about using -1 instead of +3 sometimes.
Yeah, question.
Yeah.
How come, like, for the 4n plus 2, why is knowing that, like why is that so specific? Because can't I just do that with any form of an odd number?
What do you mean? Why this is important?
Yeah, like surely it would work with 5 too, no?
Yeah.
Once it's in the form of,
Well, you could get statements similar for 5. Well, for 5 is harder because 5 is prime itself. So the only thing you could say is that it would be one of the 4 forms plus it could be 5. That's not really reducing. The reason why this kind of thing helps is later on when you talk about congruences, it helps.
Oh, okay.
Because if you consider mod 4, then automatically it's only 1 or 3 mod 4. It eliminates half of the cases you have to check. So it's more important later on, not right now.
The mod 6 example is a bit better in my opinion.
Sorry?
I think the mod 6 example is a little bit better.
There's an example of mod 6?
Well, then it's either 1 or it's either congruent to 1 or -1 if it's a prime number, mod 6. Similar to the 4.
Yeah, so yeah, well, this one also is the same thing. It's either plus or minus 1 mod 4.
Yeah, but just if I don't know, just if I did it 6, I don't know. I just find that one's cooler.
Actually, there is a theorem. I don't know if it's covered later on, but there's a theorem that talks about prime numbers congruent to 1 and 3. There's, I think it's one of the exercises. If I remember, I'll show it to you. But you actually kind of need to know congruences before we talk about that. So somebody remind me to look for that example. Right, but it does help when you get to congruences. All right, theorem 40 is one of the most important proofs in number theory, that there are infinitely many prime numbers, right? So the proof of this is proof by contradiction. So you assume that there are finitely many prime numbers, right? And if there are finitely many, let's say there are n of them, then you can list them, P1 to Pn. So what we're going to do is consider the product of those and add 1. So we're going to call that number m, capital M. Right? This is obviously greater than 1, so it must be composite or prime. Right? It has to be composite or prime. It can't be prime because Pn is the largest prime number, right? Based on what we've listed. Assume this is in order, P1 to Pn. This is the largest one, but this m is bigger than that, right? Because the product of all of them plus 1. So it's automatically bigger than Pn plus 1. So it can't be prime, so it must be composite. Right? That means if it's composite, then there's at least one of these prime numbers that divides this entire thing. But if it divides the entire thing, right, we know it divides this as well because it's one of these prime numbers in here. So it divides this, but it divides the entire thing. It means that it must divide 1. Right? That's actually easier if you write it like this. Because if it divides m, which is the entire number, and it divides this, then it divides the difference. So it divides the left-hand side. It means it divides 1. That's a contradiction because you can't have a prime number being a factor of 1. So that's basically it. All right, there's a similar proof here that all primes there are infinitely many primes of the form 4n plus 3. I'll leave that one for you all to go through. All right, this theorem is not so useful. Any positive integer n, there exists n consecutive positive composite integers. So basically, you just use the factorial to help you. Because if I take n plus 1 factorial plus 2, this is going to be divisible by 2, right? Because 2 would be a number in here. N is positive, so n plus 1, the smallest number n could be is 1, right? And 1 plus 1 is 2 factorial. That has 2 as a factor. Similarly, this thing here would be divisible by 3 because 3 would be in here, right? And then 4 would be in here, and then so on. The reason why it works, basically, you want n consecutive integers, right? So if you wanted 4 consecutive integers, it means that n is 4, so that would force the 4 to come in here. This thing stops depending on the value of n. If n was 2, right, then you would only have this thing. Right, if n was 2, then you would only consider these 2. If n was 3, you would consider these 3. If n was 4, then you will basically keep with until you stop with n plus 1. Right, there's an actual proof for this. You all could go through that in detail. All right, what do we have next? Yeah. Oh, that's it. We're almost done. So we could finish this off for primes at least. All right. This was a problem on your round 2 exam at either last year or year before. I can't remember exactly. This is an example to show you can use quadratic formula and discriminants and those things to help you with number theory questions as well. How you actually do it is if you have something that looks like a quadratic, this thing must have integer solutions. So it means that the discriminant, yes, the discriminant must be greater than or equal to 0, but in addition to that, the discriminant must be a perfect square because you can't have the square root of the discriminant being a an irrational number, then it wouldn't have integer solutions. So the square root of the discriminant must be an integer, which means that the discriminant must be a perfect square. Right? So what you do something like this is you're right. This is just one solution. You get another solution you could use. You could also solve this using divisibility if you wanted to. So you could try that. All right. So rewrite it as a quadratic in n. So bring this np across and factorize 1 minus. Where is it? Yeah. It'll be minus np here. All right. And the discriminant, remember, is b squared minus 4ac. All right. Here, well, this is the actual solution for n, but it's just the discriminant we're looking at for now. The discriminant is this thing inside here. So b squared, so that's minus p squared will give you p squared minus 4 times this. Right, so that works out to be this. For this to have integer solutions for n, first thing that must happen is this square root must be an integer. So this must be a perfect square. So I could call it m squared, where m is some non-negative integer. Now, remember, if it's m squared, m could be, if it was not 0, it could either be positive or negative. I'm going to consider the non-negative case so that I don't have to worry about considering the negative values after. I am going to choose what I want m to be, right? I'm choosing m to be the non-negative solution. And you can always do this to simplify the amount of work you have to do rather than considering cases. Because you are introducing this. This wasn't there any problem before. Right, completing the square, right? So complete the square on the left-hand side, you get this. What you can do is carry the m squared on this side, carry the number on the other side, and you have a difference of squares that you can factorize. Now here, you might say, well, okay, well, we just take consider the multiples of 296 and work with that. But that's going to be a lot of numbers to consider. So you could restrict that first of all. First of all, you know, p is prime, so this is more than 2. So this thing is positive. Right? And once one of the factors is positive, the other one is positive, right? So you only consider the positive factors of this. Now, the reason why I can do that is because I chose m to be non-negative. If m could have been negative, then you have to go and consider negative values as well. So it's important how you define m. Right? So we know this is positive, so this must be positive because the product is positive. We also know that this thing here is bigger than this. Because here I'm adding m to this and then I'm subtracting m. Again, because m is non-negative, plus m is bigger than minus m. So they're both positive. This is a bigger factor than this. And also they must have the same parity. Right? Because if you add these two numbers, you're going to get even number. Right? So it means that they must both be even or they must both be odd. So using those 3 facts, you could restrict the number of cases you have to check, right? And it's only basically 2 cases because the product is even, so they must both be even. They can't be odd, right? So where I didn't write down the factorization, but basically you have these 2 cases, 148 and 2 or 74 and 4. And then you check each case. And this case, you will get p is 77, but 77 isn't prime, so it doesn't work. In this case, you get 2 values. You get p is 41 and, well, p is 41 and you get 2 values for n that you get out. All right, so that's it for that example. Oh, this is another one that shows you how you can use the GCD, right? I didn't realize this was here either. So m and n are positive integers such that this equation is true. Prove that n minus m is a perfect square. So if I want to prove that n minus m is a perfect square, right? We can make some observations. First of all, look at this equation, right? If n was less than or equal to m, then this thing would be less than this. Strictly less than, actually, because I have 3n squared plus n and I have 4m squared plus n. So if the only way this could hold is if n is greater than m, otherwise this is going to be too small compared to this. Right? It means that this thing has to automatically be positive. So what you're going to do is let the GCD of the 2 numbers n and m be d. So then you can write m as m1 times d n as n1 times d and substitute, right? And the GCD of those two is 1. So when you substitute, we get this. This is after you simplify it. So you divide through it by d, right? So I could bring the m1 across, carry this across. So n1 minus m1 is d times this, right? Since n is more than m, it follows that n1 is more than m1. So this thing is positive. It means that this must be positive as well, right? So we'll show that this has to be equal to 1. So first, if you assume it's greater than 1, you let P be, if it's greater than 1, it has a prime divisor, right? So let P be a prime divisor of this. So P divides this, but remember this times D gives you this. It means that P also divides this, N1 minus M1. So we're going to use these two and try to figure out what P could be, right? I have two congruences and two unknowns, so that's enough to solve. Basically, you just go through the process and you get that P divides M1, N1. Now, if P divides M1, N1, right, P is prime, it divides a product, it has to divide one of them. So either it divides M1 or it divides N1. Now, regardless of which one it does divide, you know it divides the difference of the two of them. So if it divided N1 and it divides the difference, it must divide M1 and vice versa. So both of those cases lead to P dividing both of them, which is a contradiction because the GCD of both of them is 1. So that's how you prove that there is no prime divisors of this. You assume there's a prime divisor and you have a contradiction. And because that doesn't work, it means that this number must be equal to 1, right? Because it has no prime divisors and it's positive. So the only value it could be is 1. And if this is 1, it means that N1 minus M1 is equal to D times 1 from this equation up here. This is 1, so this is D times 1. So if N1 minus M1 is D, then what is N minus M? Remember, N minus M is DN1 minus DM1, which is D times N1 minus M1. That gives you D squared. So you're done. Because you prove that N minus M is a perfect square. We don't care what the value of D is. We just want to show it's a perfect square. Right, so note, this is not a direct proof, right? Because we haven't actually found any solutions to this. What we've shown is that we've shown indirectly that this thing, if there's, we don't even know that there is a solution. What we're saying is that if there's a solution, this thing has to be a perfect square, right? But the question did say to prove this. It didn't say to prove there's a solution, so you don't have to worry about it. All right, last thing I want to mention here is these divisibility tests. So these are just the tests you would use to check to see if a number is divisible by one of these. Pay attention to 11 because some people have misunderstood this test in the past. So you look at the sums of alternating digits. So the first, the third, the fifth, etc. You add those up. You add up the second, the fourth, etc. And then you subtract them, and the difference, if the difference is divisible by 11, then the number is divisible by 11. Some people have misunderstood that as being if the difference is 0. That's not necessarily the case. Right. So we'll pause here and then